Okay, now we want to look at the very special case of having the acceleration be constant. And when we do that, we see we'll be able to derive some relationships that will enable us to solve lots of different problems involving different aspects of motion. So we want to consider acceleration, and remember that we have the definition of acceleration is that the acceleration is equal to the derivative of velocity with respect to time. And of course, acceleration and velocity are both vectors. Now, I'm going to take this guy here, and we're going to consider the special case of constant acceleration. And so I've got dv by dt is equal to the acceleration. And what I'm going to do is I'm going to apply some calculus to this definition. So this is the definition of acceleration, and I'm going to apply a technique called separation of variables. And so we've got a dv and a dt, and right now they're bound together in this derivative, but in order to solve for v, we're going to separate them. And so what I'm going to do is I'm going to take this dt and I'm going to move it over to the other side. So if I multiply both sides of the equal sign with dt, the dt's here will cancel and I'll be left with a dt. So I just move this guy over here, and I've got dv is equal to a dt. And so how do I solve for v? Well, I'm just going to have to integrate both sides. And so I can draw my integral sign there, like that, and that's what I have down below. So I'm going to integrate both sides, and I'm going to solve for v. Now the integral of dv, if I say, it's amazing to me how often my students struggle if I write down, I say dv, and I say, what is the integral of that? They look at me with blank stares. But if I say, what's the integral of dx? They go, oh, that's obviously x. And so, you have to abstract what you know. You don't just want to memorize things. You want to understand the principles of things. But anyway, if we do the integral of dv, this guy there, that's just going to be v. Now remember, our assumption here, constant acceleration. So this a here, that's going to come out in front of the integral, and so I'm going to have just the integral of dt times a, and that's going to be a times t. Now, anytime you do a indefinite integral, when you have determined your integrands, you always have to add in an integration constant, usually represented by the letter c. But what we end up with is this formula here, v is equal to some at plus some c. Now that's a constant that we're going to have to figure out what that constant is. But right now, what we've done is we've taken our definition of acceleration, dv by dt equals a, we did separation of variables, we integrated both sides, and then we solved the integral equations. So now we want to see how we can take care of this constant c. What can we do to handle that? And so we're going to do what's called applying an initial condition. An initial, that just means beginning. So you could think of it as the condition at the beginning of the time. And so we're going to take the time 0, and we're going to say at t equal to 0, I don't know what this velocity is, but we're going to call it the initial velocity, and we'll call it v sub 0 because that's at time equal to 0. And so the initial velocity, the velocity at t equal to 0, is going to be a times 0 plus c. Now, of course, when you do that, that whole term there goes to 0, and you're left with the initial velocity equals to c. And that gives us the answer for what our c is. The c is the velocity when the time is 0. And I can take that c and plug it back into my equation, and that leaves me with what's in this yellow box here, orange box, whatever color it is. That is v is equal to v naught plus at. And this is our first kinematics equation for constant acceleration. So what this really is telling me, this is the velocity of the object that's accelerating. So by definition, if it's accelerating, its velocity is changing with time. And so this tells me what the velocity is at any time t. If I want to know what the velocity is at 3 seconds, I plug in t equals to 3, I do the algebra or the arithmetic, and I just get my answer. Now, some people like to think of this as the final velocity, and so very often you'll see this equation written like v final equals v initial plus at. And that's fine. And a lot of problems, you have an initial velocity and a final velocity that you're working with. But if you only think of it that way, it can be a little bit mentally limiting, because I want you to always remember that this is a function and it tells you the velocity at any time t. That includes the initial time. What is this if I plug in t equal to 0? Well, obviously I would just get v naught, the initial velocity. And so I can plug in any time here. I can get the initial velocity, the final velocity, and any velocity in the middle between those 2 points. Now let's look at a graph of this equation. And here's our equation that we're graphing up here in the corner of the graph. And so this is our velocity as a function of time, and we're plotting velocity on the y-axis and time on the x-axis. And so if I look at this equation, v equals v naught plus at, that looks very similar to y equals b plus mx. And that is, of course, the equation for a straight line. So we see that when we graph this, we do, in fact, get a straight line. And we can also use what we know about this equation for a line, because we know that this b represents the y-intercept in a normal line graph. Well, that corresponds to this v naught, which would be the v-intercept. But what does v naught really mean? That is the velocity when the time is 0. So right here, the time is 0. That's what our velocity is. Now, the other thing in this that we can correlate is the acceleration, because that's going to correspond to the slope. And so we know that if I look at this straight line and I look at the rise over the run, so the rise would be delta v, so I'm going from some v here to some v there. There's a change in velocity, delta v, and I'm going along the time axis here, so the run would be my delta t, so from some initial time to some final time. If I take the slope as delta v over delta t, well, that's just the definition of acceleration. A average is equal to delta v over delta t. But we have the condition that the acceleration is constant, and so that means that the average a is going to be the a at every time. That's just a. And so on the special case when the acceleration is constant, a is equal to this slope, the rise over the run, delta v over delta t. Now we have used this separation of variables technique to derive this equation. This is the velocity as a function of time. And we're going to apply the same trick to this equation and get an equation for the position as a function of time. Now remember, the definition of velocity, instantaneous velocity, is dx over dt. And so I've got dx over dt equals to v. That's the definition of velocity here. If I separate my variables again, so I'm going to take my dt and I'm going to move it over there. That leaves me with dx equals v times dt. But what's v? We just saw that v is equal to v naught plus at. So I can plug that in here and I can say that my dx is equal to v naught plus at all times dt. Multiplying all that out, and then to solve for x, I'm going to do the integral of every term. And so I'll integrate here and here and here. And I just want to remember, v naught and a are constants. V naught is the initial velocity, 0 meters per second. It starts from rest. 10 meters per second. It's already got some velocity. But whatever it is, it's just going to be some number, some constant. And that means that we can pull that out of the integral. This a, we can also pull that out of the integral. And so this is going to be an integral over dt, and this is going to be an integral over t dt. So when I do those integrals, I'm going to have this v comes out, and I've got the integral of dt, that's just t. And the integral, this a is going to come out of the integral, and I'll have the integral of t dt, that's t squared over 2. The integral of t dt is t squared over 2. And so if I plug all of these in, I get that my x is equal to v naught, the constant initial velocity, times the time, plus 1/2 the acceleration times the time squared. And then, of course, because these are indefinite integrals, I have to add in my constant of integration. But we already know how to get this value for c. We just set up an initial condition. Let x naught be the initial position, the starting position, or the position it has when the time is 0. And so I just plug in 0 for the times, and that leaves me with x naught is equal to c. And I can take that c, plug it into here, and that gives me with my, I end up with this blue box circling my second kinematics equation. Now, x represents the position at any time t. This is the initial position, the initial velocity, the acceleration, and then of course t represents the time. So all of those plug into that equation, and it will give me the value for the x at any time. And of course, again, that could be a final position, it could be an initial position, it could be any position I want. I just have to plug in the appropriate time, and that'll tell me what the position is. Now I have my equation here for x as a function of time. This is the position at any time t. And if I look at that, it goes to t to the squared power. And that is the highest order of that equation. And this whole equation is the equation of a parabola. And so if you have a constant acceleration, and again, both of the equations we've derived so far, the one for velocity and the one for position, they only work if the acceleration is constant. But if the acceleration is constant, those two equations are valid. And so we know that if the equation is constant, the position is going to move like a parabola. And if I graph x as a function of time, I would end up with a graph that looks something like this, something parabolic. Now, there's a third kinematics equation that we're going to derive that is quite useful, and we're going to derive it using the chain rule from calculus. Now, remember, the chain rule works if you have a nested function. If you're taking the derivative of a function that itself depends on a second function. And so the classic example would be something like if I did the function y equals to the sine of some alpha t, and you want to take the derivative of that, you take the derivative of the whole function, which would give you cosine of alpha t, and this would be my y prime here, and then you take the derivative of the inside, which would be alpha. And so I would end up with my y prime would be alpha times the cosine of alpha t. And that's how the chain rule works. You take the derivative of the outside function and you multiply it by the derivative of the inside function. Well, you can write this using the differential Leibniz notation. And so what I have here is an equation for dv over dt equals to a. And I've expanded that out using the chain rule. So I've said that dv over dt equals dv over dx times dx over dt. Now, what does that mean? Let's look at the picture up above, because I want to understand what all this symbols mean. So I've got this box here, and it is accelerating to the right, and it's got some initial velocity. And so it's going to be moving some x distance, and it'll end up over here somewhere after some amount of time. And so we can say dv over dt, that's going to be the change in velocity over the change in time. But it's not just moving with respect to time, because I could say, what's the velocity as a function of time? I could say, what's the velocity at 1 second? What's the velocity at 2 seconds? What's the velocity at 3 seconds? But it's also changing its velocity as it moves along the x-axis. And so I could say, what's the velocity at 1 meter? What's the velocity at 2 meters? What's the velocity when it passes 3 meters? You guys get the idea? So I can say that the velocity depends on the time, or I can say that the velocity depends on the position. But if I choose that second option, I say, what's the velocity as it depends on position? We have to be aware of the fact that the position is also changing with time. So the velocity depends on position, but the position depends on time. And so you have a nested function. And so if I want to take the derivative of v with respect to t, I have to take the derivative of v with respect to position, and then the derivative, that's the derivative of the outside function, and then this becomes the derivative of the inside function, the derivative of position with respect to time. And you can almost think of it like these dx's, they would like cancel out and you'd be left with dv by dt. but both this and this have to equal the acceleration. So we're going to use this formulation to derive another relationship. Basically, what we want is what's the dependence of the velocity as you change position. That's the goal. So this is our alternative form of writing the acceleration using the chain rule. And so I'll just write that in because it's important that we are using the chain rule here. And if we look at these terms, we've got dv over dx times dx over dt. But if we're clever, we'll recognize that dx over dt, that's just the definition of velocity. And so if I plug in velocity for this guy, I end up with the acceleration equals to the velocity times dv by dx. And so now I've got a v dv and a dx. I can do the separation of variables again. And so I'm going to take this dx and move it over to the side with the a. And now I've got a dx is equal to v dv. And I can integrate both sides to solve for v, which is what I want. Now, so far, we have done these integrals as indefinite integrals and then gotten an integration constant, and then we had to apply an initial condition to solve for the complete equation. But there's actually another way you can do this. And so I thought on this example I'd show you an alternative approach to that, and we'll look at that. The alternative approach is to simply plug in the limits if we know what they're going to be. And so I've got the left-hand side of the equation, a dx. Well, I know that I'm starting at some initial position, which I'm going to call x naught, and I'm ending up at some final position, which I call xf, and those are the limits of my integral. And then my v, I'm starting at some initial velocity. I know I'm accelerating, my velocity is changing, and so I'm going to end up at some final velocity, and so those are going to be the limits of integration. And of course, these integrals are pretty straightforward. This integral is just a dx, and then you put in your limits of integration, which would be x final minus x initial. And then this becomes v squared over 2, and I'll put in v naught and vf as my limits of integration, and that gives me 1/2 v final squared minus v initial squared. And I want to solve for v final squared, and so if I do that, I get what's in this pink box here. The final velocity squared equals the initial velocity squared plus 2 times the acceleration times the change in x. And that's our third kinematics equation. Now the last equation that I want to look at is sometimes considered the fourth kinematics equation. It's less useful than the other relationships, but occasionally it's something that you would want to know. And this equation works out to be that the average velocity over some time interval is going to be given by the final velocity plus the initial velocity over that time interval divided by 2. Now, we can see how that works by looking at the graph of the first kinematics equation. So this was our first kinematics equation. We've already seen how to graph it. And we're going to assume that we start at t equal to 0, and we have some initial velocity, and we go to some final time, at which point we have a final velocity. Now, if I average those endpoints, the way you average that would be v naught plus vf divided by 2. And so this would be the average of those two endpoints. Now, what's interesting is that that average, I think it won't be hard to convince you, is going to be right smack dab in the middle. And so there would be some v average right there in the middle that you would have to have. Now, what about the other points on the line? If I consider a point above the average is going to bisect that line. It's going to be right in the middle. And so if I pick a point above the average, there has to be a corresponding point the same distance below the average, and those 2 points together are going to average to the middle. And so every point above the average has a corresponding point below the average. They all have to average together to the middle. And so this equation here, v average is equal to v final plus v initial over 2. That's not just the average of those two endpoints. that's the average of every point on that line. And so this is a generically true equation that the average velocity over the time when an object is accelerating with a constant acceleration is equal to the final velocity plus the initial velocity divided by 2. And so that's kind of cool. So here I have a summary of the 4 kinematics equations that we've covered in this video, and I've put them in order. It is important that you guys memorize these equations. I don't make you memorize a lot of stuff in this class, but these 4 equations, you just need to memorize them. Know them like the back of your proverbial hand. And also, I want you to learn them in this order. So this is the first, this is the second, this is the third, this is the fourth. So in the future, when we're talking about some object that's moving, and I say we can use the second kinematics equation, you should know which equation I'm talking about, and you should know it well so that you have an image of that equation in your head, so that you can work with it, or at least be able to write it down so that you can look at it and see what I'm talking about. So anyway, these are the 4 kinematics equations that apply when the acceleration is constant. Memorize them, learn them, love them, know them like the back of your hand. And in the next videos, we're going to be applying these, and you'll see that you can apply these equations to lots of different situations.